So, I'm Saurabh Pofle from Oak Ridge National Lab in the Programming Systems Group. So are the other two authors on this paper. And this ChatPORT, as I mentioned, is intentionally meant to sound like chat something. And the port part is the porting. So people wonder, is it portability? What kind of, if it is a library or something. So I'm going to go with the basics. We all know this. What are LLMs? These are basically deep learning models trained on massive data sets, open, everything that is available to them. They take it, they capture patterns of data generation. They can summarize very well. They translate and they can reason over data, and you can kind of have a dialogue with an LLM at this point. Examples include all the GPTs, Llama, Palm, Code Llama, and we have seen various applications, and they are increasing day by day. So code generation, scientific writing, summarization, reporting, creating graphs, in my case, LaTeX debugging. So it has a lot of uses. So why fine tune? Fine tuning is basically taking a base LLM and then giving it data to make general purpose LLMs more specific for a particular task. And they will do work, they will become much better at that task. It enhances the accuracy, reliability, and the domain alignment. And you can also teach it domain language, which may not be available out there. We work in a very niche field, and it is not obvious to LLMs because our data is very small compared to everything else available out there. So LLMs might not know about it as much. So the concept of fine tuning existed before deep learning, and it's been evolving since the 1990s. What we have currently, what we call fine tuning, was brought about by Howard and Ruder in 2018, and they kind of invented the modern natural language processing fine tuning methodology, which was much more refined by BERT in 2018. And that is where, from there on, we've started seeing more of this fine-tuning effort, and it has come into mainstream HPC since 2023. So, benefits of fine-tuning. Higher accuracy, you can capture vocabulary, like I mentioned. Efficiency. Now, this is another aspect. You can use a smaller curated data set to fine tune. You don't have to have millions and millions of data samples. So if you have a smaller set of representative, in my case, kernels, it is enough to teach it, specialize it for a particular task. So it makes it very attractive because you want it to do a certain thing, but you don't want to waste time, collecting data and formatting data and massaging that data into usable formats. So fine-tuning strategies broadly fall into two categories. There is a full model fine-tuning and a parameter efficient fine-tuning. Here, this work, we do the parameter efficient fine-tuning. And the full model fine-tuning involves updating all model parameters. So, and it is very expensive, both in terms of time and the computational power it requires. It leads to higher accuracy, but we've also seen cases where it causes overfitting. Well, we are looking at a problem where we have limited memory, we have limited computational sources, we don't want to explode our data. And within these constraints, how can we get the best output from a fine-tuned LLM? So our motivation for ChatPORT was that we have seen the evolution of different programming models. We have CUDA, HIP, which are very platform specific. Then now we have our portable models, OpenMP, OpenACC, COCO, SYCL, what have you. And although people want the best performance, they are also looking at performance portability. So they always want to have something, they will have one branch in OpenMP, they will have one branch in CUDA. But what is happening is that people do not want to invest a lot of effort in porting applications. So we are trying to give them a high fidelity option to go from one programming model, one accelerator-based programming model to another. So this is, again, like I said, it's low cost, quick, effective. And our first experimentation, so this is an interesting story. So from our group, Pedro and Aaron, they built up a quick way to fine tune on one of our compute systems. And we're like, okay, all of us tried it. And I was curious. So I also tried it for, I tried it for CUDA to OpenMP, and Zeming tried it for CUDA to SQL. And we saw much better result. And at that time, we were just using Code Llama, the 7 billion model. And we're like, hey, this is neat. And that time we didn't even have enough data. And even with a small data set, we saw good results. And we're like, we need to investigate this further. So that's what got us started on this. And we're like, okay, how do we choose a base model? And this paper is all about that. So what is the starting point? How do we choose the base model? How do we set up our data? And how do we evaluate? So there are two main components to this, obviously, the training data and the base model. So the training data, we picked it up from Heckbench, and also from the OpenMP validation verification suite. We curated from different domains to have enough representation across the scientific pool of applications. And the the kernels are also from Heckbench, but there's no overlap between the training data and the test data. So the training set, now this was a little work we had to do. Well, you have to put it, we use the JSON format, and we have to put it in the question, context, and answer. We used a very simple design. You can add much more to this, to add more meat or to add more context or connections. But we started with a very basic format. We went from there. And for supervised training, we were like, okay, let's start with the simple and then add the more complex fields as we go on. So for our work, we are doing kernel to kernel translation, not full programs. So we take a kernel in, say, CUDA, and then we put it through ChatPORT, and you get a kernel, the same kernel in OpenMP. So base model. So we evaluated 5 families, 2 of each, one a smaller size, a larger size, just to investigate what are the differences we get when porting, what is the memory usage, what are the limitations of each. And ChatPORT can be, basically it's portable, like, so you can build it over any pre-trained model, because the data is what makes it ChatPORT, not the base model can change and evolve. So we chose Code Llama. This is based off the Llama model, which is now Code Llama is for code specific. Granite Coder is from the IBM family of trained models, and it is being trained over a large number of programming languages. Star Coder is a product of ServiceNow Research and Big Code Initiative. So it is developed for engineering and coding. So HPC Coder, Quinn 2.5 Coder, same thing. It's the common feature across all of these are open models. We can use them, we can share our results, we can collaborate over them. We didn't want to use anything proprietary or closed source that we could not do open research on. So a quick note about the setup. Too many details here, but I just wanted to keep it there for people who might be interested. So we're using PyTorch, we use the Hugging Face trainer. A trainer basically does the data handling, model optimization, resource management, and evaluation and logging. So all the trainer does all that. And we use QLoRa, which is a combination of quantization and the LoRa. LoRa has been there. What quantization does, it is reduces the precision of the model without affecting the accuracy. So you are trying to reduce the memory usage. Think about it that way. And then we have the AdamW optimization, the learning rate, if anyone is interested, 400 steps, we do 100 steps of them are for warm up. The batch size is 8. 8 is considered medium for our data sizes. And we chose that because that gives, it's just about enough information without causing overfitting with the model. And yeah, so what is temperature? Temperature is basically you're telling the model how much it can, how much creativity it can add. So a lower number means you're being more strict. Say, follow these rules, don't diverge too much. But if you wanted, if you were doing something which, you could go get creative about, maybe that is natural language processing, writing an essay or something, you would set the temperature higher, then it would create connections where it more than it would in this more constrained environment. So this is the final fine-tuning process. We created the data, we picked an LLM, we use an inference script, Python, to fine-tune the model. We get a ChatPORT variant. You can take CUDA, SQL. Right now, we also have SQL features, and then you will get an OpenMP, CUDA to SQL or OpenMP. Here we are focusing only from CUDA to OpenMP. So let's look at the training statistics. Why are these important? These models all are the 7 billion parameters, 13 billion parameters. They will take different, they are obviously of different sizes. The total parameter count is different. The trainable parameters are different. And what percent of the parameters we are training, it's less than 1%, right? So with 1% of parameters need to be trained, and depending on the size of model, the training time was between like 8 minutes to 100 minutes. That was, so it's very feasible. That's what I'm trying to say. So the evaluation loss is important. You want the evaluation loss to be as low as possible. That tells you that the model is being fine-tuned on highly specialized domain with high prediction confidence. So you have to always check on the evaluation loss. So memory usage. This is the peak GPU memory usage across all the models. The general expectation is bigger model, more memory, which was not always true. So we see that the trend is that way, but a 15 billion parameter model consumes nearly 96 GB, if I remember correctly, on a single GPU. But fine-tuning the model with 10 times fewer parameters just takes 40% of the GPU memory. So it matters how many parameters you select to fine-tune. Interestingly, the Qwen 2.5 coder, it utilizes more memory than the much bigger models. And we did a little bit of profiling, and we found out that most of his compute was going into, the memory usage was going into cross-entropy loss, which is one part of the evaluation part. So now at this point, we have all the variants of ChatPORT based off different LLMs. We have fine-tuned it, and now we need to evaluate these variants. So we tested with the CUDA kernels, and you will be surprised that the training and the evaluation split is kind of the other way around. Usually people use 3/4 of the data to train and 1/4 for evaluation, but we don't need that. And keeping the training data lean is a deliberate choice. We want to have the representative kernels out there, but we don't want to have repeat the same information. So we also built an automated validation pipeline, which was a lot of work, but thanks to Hackbench, we already had the resulting OpenMP kernels. So it was easy to compare. We use AMD Clang because on that platform, that was the one that passed most of the OpenMP features, and it was easy. So the evaluation framework, we generate, now we start with the responses from ChatPORT. They are again in a JSON file. You have to clean up, we have to extract those kernels. And from the extracted kernels, we took, since we're doing only correctness of the kernel, we kept the whole OpenMP program from Hegbench the same and replaced just the kernels with our generated kernels. And then we compile, we execute, and then we validate. It has to compile, of course, it has to execute, and the benchmark has to give the correct answer. So this is a more strict testing than most other works we have seen out there. And this is what we saw. So now these are all the base models. We did the same test before we fine-tuned them using the same test kernels. And this is the correctness rate we got before. We fine-tuned it with our curated data, and this is what you see after. It's significantly better. Not 100%, but definitely better. So we were pleasantly surprised with this. And some of them which went from like 0 to 72, that was like, oh, we want to investigate why it did not know anything and suddenly it knows as good as the Code Llama 13 billion parameter. So even with that, there were very common transpilation errors that we noticed. So these are basically the very high level classification, the built-in CUDA variables. ChatPORT couldn't understand that, okay, this is very CUDA specific. It thought it was a program variable and it just kept it in the program as a program variable. It did not go from, plugins. It could have done teams or threads or whatever. It did not do all that. Device side CUDA functions, atomic adds, it did not use, the correct directive for OpenMP. It just used it like a user function. It just took it atomic add and put it there. In some cases, it was using incorrect clauses with the directives. So on Teams, instead of using thread limit, it was using num threads. Silly things like that. But overall, they were pretty much to the point where you could, correct these mistakes and run the code correctly. And the most irritating of these were undeclared variables and unbalanced traces. This is something that, it's hard to catch. It's hard to, when you're looking at the code, you're like, oh, what's happening here? So these were some things that we found. Again, this is just like a one-shot thing. We are putting in the code and getting the code out. We're not doing any more prompt engineering with this. What we did, and I don't put it here, is that, remember the logs that we collected from the compiler and from the runtime, we took those errors, we analyzed those errors, and based on those, we found out the deficits in the knowledge of our LLM, ChatPORT. And we added more data to our training data set, and then we redid it. And we found that of these, on most of these numbers, they went up by 6%. So we can get even better if we add that feedback loop back to ChatPORT. So coming to current status, this was just one effort to see where we should start with the base model. What we are doing now is integrating support for Cocos and OpenACC and adding, we're also evaluating, we want to make this the base model. So LLMs are generated, I don't know, hundreds, thousands per day. We can't use one static base LLM. So we want to automate this model to pick up the latest and the greatest and make sure that ChatPORT is getting the best numbers out there. The other thing we're working on is adding ontology to the data. Like we started with a very basic data set, like question, context, answer, that's it. Now we are adding relationships that would enable them to make, connections with, okay, OpenMP. Oh, this is very similar to OpenACC. So I don't have to teach it OpenACC separately. And there are two other auxiliary projects, is fuzzing for validation with Oregon State University and They in Georgia Tech, they're using ChatPORT as one of the LLMs in the pipeline in a multi-LLM chain for feedback-based corrections. So they're using specialized LLM for code generation, more general purpose LLM for syntactic corrections, and so on and so forth. So, summary. Not all open LLMs are geared towards HPC, even though they say they are, and they are completely, sometimes absolutely completely oblivious of niche programming models like OpenMP. All base models we saw benefit from fine-tuning, but they learn differently. You cannot, say that, okay, this one is going to be the best at all times. No, they will learn differently, and they'll have different weights at the end of the day. Depending on the memory size, computer resources available, you can choose a different base model. It's not that only one, and that is the only one that's going to give you correct answers. You can make that trade-off between how much memory, how much compute power you have, and which base LLM you should choose. Like I mentioned, fine-tuning improved correctness by overall, it improved it by 43.2%, and the feedback increased it further by 6%. My last slide. Mandatory acknowledgement. Thank you, everyone.
Thank you, Dhruv.